Okay. So Monday we kind of refreshed the 4 characteristics of SN2. Are there any questions about SN1? Because that's what we were going to do. That's what I was going to talk about today.
Can you just go over how to draw the mechanisms? I'm a little confused on how to based on
the mechanism of SN1.
I mean, just the mechanism.
Right. Yeah. That's going to be the second characteristic. Okay. What else for SN1? Bless you. So first of all, as I kind of left off on Monday, the rate equation for an SN1 reaction is to have the alkyl halide to the first power and the nucleophile to the 0 power. Anything to the 0 power is 1. So what that meant was that when they did the experiment, they found that if they doubled or tripled the concentration of the nucleophile, it had no effect on the rate. Whereas if you double or triple the concentration of the nucleophile in SN2, it doubled, tripled the rate. So that whenever there's a change in kinetics, it tells you that there's a change in mechanism. So then you end up having to propose a mechanism that will fit this rate equation. So let me start with, so that's characteristic number 1 is the rate equation. Characteristic number 2 is going to be, well, what's the mechanism of this? The mechanism of this is going to be slightly more complicated because we're going to have to talk about transition states, intermediates, etc. So let me start with something that's as simple as this. Let's take a tertiary alkyl halide. Let's take like a tertiary bromide and let's add to it chloride. Now, when you do this reaction, you're going to find that you get substitution as the final product. You get the same substitution product. And they got that and they said, oh, well, this is the same mechanism as if it was a secondary or a primary halide. But then they did the kinetics on it and found that the nucleophile didn't have a role. So my number 1 question would be, why is this not SN2? Can't the chloride decide to come and attack from the backside and kick the bromine off? Stop there, don't question yourself. So with the tertiary halide, there's a lot of steric hindrance there. And so the reason this can't be SN2 is because this is a tertiary halide, and tertiary halides have too much steric hindrance for the nucleophile to attack. Okay. So there must be an alternative mechanism because I get the same product. I just get it by a different rate equation. So we have to propose a rate equation that makes sense. Now, this is what's called the overall reaction, right? The overall rate equation, which was determined by experiment, was that it was the rate times a rate constant times concentration of the alkyl halide to the first power. Okay. So a one-step mechanism can't be the case, because if it was a one-step mechanism, the nucleophile concentration would be in the rate. So it can't be. It's got to be multiple steps. So for step number 1, what was proposed was that your alkyl halide, the carbon-bromine bond breaks, and we form a carbon that only has 3 things bonded to it and a bromide. So looking at this, if the carbon-bromine bond breaks, the electrons are going to go with the most electronegative element, which is the halogen. the carbon's going to lose an electron because the pair went to the bromine, and so the one electron that the carbon owned here is gone. That gives it overall a positive charge. And so this is what is called a carbocation, or it can also be called a carbonium ion, but I like the carbocation term better. And that just means the formal charge on that carbon is +1. Okay. Now, whenever we write a mechanistic step or a mechanism, we wrote the transition state for SN2. We need to have a transition state for this first step. So we're going to write the transition state the same way that we're going to use a similar methodology to what we use to write resonance hybrids. We're going to have dotted lines, we're going to have delta charges. And so the first thing that we have to do is we have to write this structure showing what bond was broken or what bond was made. And in this case, it's the carbon-bromine bond that's being broken, and that needs a dotted line. So in the transition state here, between the products and the reactions, I have a partial carbon-bromine bond because the carbon-bromine bond is breaking. Okay. So you could average this out: carbon-bromine bond, no carbon-bromine bond, average, partial carbon-bromine bond. So then we need to do charges. Carbon 0, carbon +1, average, delta plus. Bromine 0, bromine -1, bromine's average, delta minus. And so that would be our transition state for this reaction. And the transition state is the peak on the energy curve. As I go from reactants to eventually products over here, each peak is a transition state. Transition states cannot be put into bottles and studied. They're too high energy species. Okay. So that is step number 1 that we can propose. Okay. Then that doesn't give us the final product, so then we have to propose step number 2. And step number 2 is going to be to take the alkyl halide, to take the carbocation and react it with the Cl-. And the Cl- basically has an octet, 4 lone pairs. The carbocation is electron poor. It is incredibly electron poor, which makes it an electrophile. Electrophile means negative loving, but electrophiles are electron poor, so they're going to react with something that's electron rich. What's electron rich? The chloride. Why? Because it's got lone pairs. By having that extra lone pair, it's got a negative charge. So what's going to happen is the chloride's going to take its lone pair, it's going to donate it to the carbon to form the carbon halogen, in this case the carbon chlorine bond, and that will be no charges. It's 0 overall. Okay. So this is what we call our nucleophile. What would the transition state for this look like? The transition state would have a partial bond being formed between carbon and chlorine. So that gets the dotted line. The carbon's going from +1 to 0, so it has a delta plus charge. The chlorine is going from -1 to 0. It gets a delta minus. And so that would be the transition state for the second step. And then for these mechanistic steps, if we add them up, so if I added step 1 and step 2, I'm going to get the overall reaction. Okay. So if we go back and we look at the reaction coordinate diagram, after you form the first transition state, the energy goes down, but then it forms the carbocation intermediate, goes into a second transition state, and then to the final product. So that would be the reaction coordinate diagram for this reaction. It has two transition states and two peaks, one valley. What's the valley? The valley is what we call the carbocation, and it would be called starts with I, intermediate. So intermediates are the species that are formed in one step and react in the other step to form the final product. So intermediates are the valleys. Now they still have a high energy, but the difference between a transition state and an intermediate is the intermediate could possibly be placed in a bottle and studied. Not all of them. Some of them are really super unstable, so we can't study them, but other ones we could. And so the carbocations, it's possible to form them. It's possible to study them with different instruments. And so that's the difference between transition state and intermediate. You can never study a transition state because it's not around long enough to study. Okay. All right, so that's our overall two-step mechanism that people proposed. Now, to go along with their proposal, there's going to be a lot of questions that are going to be asked. Number one, does this proposed two-step mechanism match up with the overall kinetics of the reaction? So let me do this. Let me just write a generic reaction here. And step one will be to have the alkyl halide bond break to form the carbocation and the X minus. And then the second step will be for the carbocation to react with the nucleophile to form the final product. The overall rate equation up here, just to complete it, was that the rate was dependent upon the concentration of the alkyl halide to the first power. Now, when I teach general chemistry, which is averaging now about once every 10 years, although when I first started, I taught it every year, so people had me for two years straight. Some chose to, I guess. Some were forced to. When I talk about kinetics, I know that I'm going to be talking about kinetics a year later. So when I look at kinetics, I say, remember that the overall rate equation has to come from an experiment. Right? I need to take my alkyl halide, my nucleophile concentrations, change them one at a time to get that overall rate equation. It has to come from experiment. And you might say, well, what else could it come from? And then I have to say, it does not come from stoichiometry. Right? Yes, there's one nucleophile with one alkyl halide, but that is not the reason these are to the SN2 reaction is to the first power in each. So we do not use stoichiometry, although it can happen. For the overall rate equation, it has to be done experimentally. Then we go and we write a mechanism. And these mechanisms have elementary steps, is what I call those two mechanistic steps. They're elementary steps of the mechanism. Well, the rule's a little different if you want to write the rate equation for an elementary step of a mechanism. Because you don't need experimental data for that, I can just write that based on using the stoichiometry. So it's a little confusing because why can I do it for elementary steps? Why can't I do it for the overall reaction? Because the elementary steps are my proposal. The overall reaction is real. So until I know what the mechanism is, I could propose lots of things. So in this case, what I would say is, well, the rate of this elementary step is K times the concentration of the alkyl halide raised to the first power, and now that number 1 is because of the stoichiometry. And I'm allowed to write that because it's an elementary step. And I could come down here and I could say, well, the rate of this equation is equal to K times the concentration of the carbocation times the concentration of the nucleophile, both of those to the first power because it's one molecule reacting with another. Now, those two elementary steps do not have to occur at the same rate. And how would I know which elementary step was faster, which one was slower? The way I do that is that the slowest step, its rate equation, is going to match up with the rate equation overall that I determined experimentally. So the slowest step should have the rate equation that equals the overall equation. Right. Down here, if step number 2 was the slowest step, the concentration of the nucleophile would show up in the overall rate equation. It does not. Okay. So that must mean it's a faster step. And so the overall rate of the reaction is based on what is the slowest step. The slowest step is also called the rate determining step. So this would be also called the rate determining step. And so for this reaction, if I said, okay, here's my proposed 2 steps, I would say, I think I'm right because in this case, the slowest step has a rate equation that equals the overall rate equation. Or better yet, I proposed a step where its rate equation equals the overall rate equation. If I propose a bunch of steps and the rate equations don't equal the overall one, they're probably not the correct steps. So this is what people proposed, and then we say, okay, what's happening in this reaction? The carbon halogen or carbon leaving group bond is breaking, broken. Nucleophile adds. So slow step, fast step. Okay. So that's what people proposed, and they said, well, that's why I think I'm right. Now, whenever you propose mechanisms, if it's going to be something brand new, you can never, my PhD advisor used to say, well, you can never really prove a mechanism. All you can do is try and do everything you can to disprove it. And then at some point, that's all that's left. Because science being fairly competitive, if you don't try and break or if you don't try and destroy your proposed mechanism, somebody else will. In a probably not very nice fashion, right? So you try and break it, or you try and get evidence to support that mechanism. Well, if I'm going to propose this mechanism, the key to this is the formation of that carbocation. So people are going to then start to ask me, they're going to start saying, okay, there's this carbocation intermediate. Can you observe it directly in solution? And the answer is actually yes. The person that did that is George Olaw. He was at CASE when CASE was called CASE Institute of Technology. He was the one that was able to protonate a methyl group to form the carbocation. He dealt with super acids that could protonate anything and make carbocations. He was a friend of my PhD advisor's. I've heard him speak once. That's what he won the Nobel Prize for, was all his work on carbocation chemistry. So can you observe them? Yes, you can observe them. What are their features? For instance, we could have a tertiary carbocation, we could have a secondary carbocation, we could have a primary carbocation, we could have a methyl carbocation. Which one of those is the most stable? Tertiary? Do we agree it's tertiary? It's tertiary. So having 3 alkyl groups is attached to the carbocation is going to make that carbocation the most stable it can be. Now, it's not tremendously stable, but it'll make it more stable than a methyl group. So tertiary carbocations are the most stable. Second most stable are secondaries. Primaries and methyls, carbocations do not form. I'm going to have to qualify that. They do not form in solution this semester in lecture. They will exist next semester in lab when we're talking about mass spectrometry. The difference is that mass spectrometry is done in a high energy, heated gas phase environment where there's tons of energy. They can exist all day long there, but not in solution. So if we have rules of do not do this in organic chemistry, this is rule number 3. Number 1, take it. Number 2, 5 bonds to a carbon. Number 3, no primary carbocations in the solution phase, which means no primary carbocations in lecture. Lab will be okay. So, study carbocations, we find that tertiaries are the most stable, and then we have to ask ourselves why. What's stabilizing a tertiary carbocation? Well, it has to be the added alkyl groups, because the more alkyl groups I add, the more stable the carbocation is. But that's a correlation, that's not a reason. So I'd have to ask the question, carbon-hydrogen bonds are relatively nonpolar. But if I had to put a delta positive charge on one of those 2 atoms and a delta minus on the other, who gets the delta plus charge, carbon or hydrogen? Take a guess. Somebody take a guess. Good guess. That's correct. So hydrogen gets the delta positive charge, and chlorine gets, and carbon. Well, chlorine would definitely get the delta negative, but carbon gets the delta minus. The electronegativity difference is hydrogen is 2.1 and carbon is 2.4. Do you have to memorize that? No, I've been doing this a long time. I've memorized it. So carbon is slightly more electronegative than hydrogen. 9 times out of 10, we call it a covalent bond and move on. This is the one time when we need that difference. So what does that mean? That means every alkyl carbon, every carbon of the alkyl group has a little extra electron density. Where did they get it from? The hydrogens that are attached to them. What can they do with that negative charge? They can push it into the carbon that needs electron density. This carbon is in bad shape, right? It would like to be at 8 valence electrons. It has 6 shared. That's not good. 7, when we get to 7, when it has 7 valence electrons, a primary actually can exist. But with 6, primary is too unstable. Anything I can do to push a little bit more electron density into that carbon is going to make it more stable. And so that's what I do. So in this case, every single alkyl group that's attached stabilizes the carbocation a little bit more. And so 3 is best, 2, okay, 1, not enough. And methyl, there's no hydrogens there, or there's no carbons there. So methyl carbocation is going to be super unstable. So when we're talking about this intermediate, and I'm trying to prove my mechanism, eventually I'm going to have to know as much information about that intermediate as I can. The other thing I need to know is structure. So when you have a carbocation, it has 3 sigma bonds. What's the hybridization of that carbocation? It's got 3 sigma bonds, no lone pairs. It's going to be sp2. So the carbon's going to be sp2 hybridized. I still got an unhybridized P. What's in that unhybridized P? It's empty. There's nothing in that unhybridized P. It's empty because that's what gives the carbon a plus charge. We'll talk about radicals later. Radicals have, maybe we'll get to radicals by the end of the semester. Radicals have 1 unpaired electron in the p orbital. But this has nothing. Why is that important? Yeah, so hyperconjugation is another way to say that the C is pushing electron density into the carbon. Hyperconjugation, which the book apparently talks about, says that if you have an alkyl group attached to the carbocation, you can align the sp3 orbitals parallel to the empty orbital. And so when I say over here that it's pushing electron density in, this is the exact mechanism by which it pushes the electron density in. And you can only push electron density in from an alkyl group by orienting its sp3 parallel to the empty p. But if there's no carbon there, there's no sp3 orbital to push electron density in. So this is more of a direct, and so hyperconjugation is the mechanism by which it pushes electron density in. So there's 2 empty lobes. That's going to come into play because when in step 2 here, the nucleophile reacts and adds its pair of electrons to the carbocation. So I'm the nucleophile sitting over here. Here's my lobe. Here's my pair of electrons of my, that make up my negative charge. Just like in SN2, that lobe has to overlap with another lobe to form the bond. So I'm sitting here as a nucleophile. I see 2 lobes. Do I add to the top lobe or do I add to the bottom lobe? Either one. There's nothing there. So in this lobe, there's nothing. There's no electron to spend 50% of its time. I like 50%, but not for that reason. Is there anything that's stopping the nucleophile from adding to the top or adding to the bottom? No, there isn't. So that means that the nucleophile is going to add to the top 50% of the time. It's going to add to the bottom 50% of the time. If in doing that, it makes a chiral center, then what happens? Then in this reaction, I would get a 50% R configuration of the product, 50% S configuration. And that mixture, that 50-50 mixture would be called a racemic mixture. Okay. Yes?
So you said there was nothing preventing it from going into either the orbital.
Right.
What would prevent it?
Maybe there's something blocking it on the top versus the bottom. What will tend to maybe stop it would be if there was a chiral center attached to that C+, and that chiral center maybe had one orientation of like a methyl or ethyl group that might sterically keep it from adding to the top versus the bottom. But unless it's a chiral center, it's just going to add 50-50. There's going to be nothing, there's no sterics there preventing it from adding to either one. So it's going to add to both equally. And so what this means is, remember that when we took a chiral alkyl halide and we did SN2 on it. It came in backside attack. We got a chiral product, and that the chiral carbon underwent inversion of configuration. In this case, if I take a chiral molecule, a chiral carbon, the minute it loses the halogen, it becomes achiral. And so the nucleophile adding top and bottom would give me a racemic mixture. So when people proposed this mechanism, one of the things they said was, if your mechanism is true, then when you take a chiral halide and you do the reaction, you should get a 50-50 mixture of enantiomers. And if you don't, then your mechanism is busted. Which means that you do the experiment, you start with a chiral molecule, you measure its rotation, you do the reaction, you get 50-50, they cancel, and you get no rotation. And so you say, I got no rotation, therefore I have a racemic mixture. And then somebody says, show me evidence that you actually have R and S there. So then you got to show them R and S, which has been done. So our characteristic 3 of SN1 is when you have a chiral molecule, you get a 50-50 racemic mixture of enantiomers. Characteristic number 2 is this mechanism. So we have to talk about the intermediate simply because we have no choice. If you're going to propose a reaction with an intermediate, you better have good evidence that that intermediate exists, and you better know everything you can know about that intermediate, including stability and structure. So it's taken a number of years for us to get to the point where this mechanism goes into textbooks. All right, everybody kind of with me? Anybody super bored? Probably wouldn't be a good thing to say, because then I'll have to ask a question and unbore you. So those are the 3 characteristics then. Now what's the 4th characteristic?
So do you mind repeating again what the 3 were?
The 3 were. Number 1, the number 1 characteristic was, number 1 is the rate equation. Number 2 is the mechanism. Which is 1 step, then the 2nd step. The third characteristic then is what happened with a chiral alkyl halide. So in this case, the 3rd characteristic is that when you take a chiral halide in an SN1 reaction, your product is a 50-50 mixture of R and S. And so you do not get a chiral product because it's a 50-50 mixture. You end up forming a racemic mixture. Okay. So that's number 3. And then I believe number 4 would be reactivities of the alkyl halides, right? So which alkyl halide reacts fastest in an SN1 reaction? Primary, secondary, tertiary. Tertiary reacts faster than secondary, which reacts far faster than primary because primaries do not undergo SN1. Why? Because they can't form a stable carbocation. But that's okay. If you're a primary halide, what can you do? If you're primary, you're not sterically hindered, so the nucleophile is just going to come in and directly attack you. So you can still undergo substitution, it's just you'll use a different mechanism. The same thing was true for the tertiary last time. The tertiary couldn't undergo SN2, but that's okay, it can undergo SN1. Now, if it starts out chiral, there's no way to keep its chirality. But I can't get around the steric hindrance.
Did you say that the tertiary was fastest or slowest?
Fastest. So this is the fastest, and then second fastest is secondary, and primaries don't undergo. Now, I feel obligated to have a discussion here about why is the tertiary, why does it undergo the fastest reaction? In a fairly logical, but you're going to say far too complicated manner, no, we're going to do it anyway. So, we find experimentally that tertiaries react the fastest. Why? Y has to do with the following. The rate determining step of the mechanism, right? Our rate determining step that we showed up here, our rate determining step, which is not that one, which is this one, that rate determining step is the slow step of the reaction. So, my question would be, what do you think, with your gut instinct, what kind of carbocation do you think will form fastest? Tertiary. That should probably be the obvious answer because, well, whatever reaction occurs fastest is going to have the fastest rate determining step. So if you already told us experimentally it's tertiary, then it's got to be tertiary. So let me restate the question. If I had two intermediates, so I start out with my reactant, I'm going to have two different intermediates. And my energy goes up. So the intermediate at the higher energy is going to be less stable than the intermediate at the lower energy. Right? Basic chemistry principle, the more energy you have, the less stable you are. The less energy you have, the more stable you are. I don't know how that works with people, but you could figure it out. So more stable means less energy. Then I have that more stable intermediate, so I know that a tertiary carbocation is more stable than a secondary carbocation. So the issue here is why? Why would you form the more stable intermediate faster than the less stable intermediate?
Or it takes less energy?
Yes, it's going to take less energy, but it's going to take less energy in what kind of energy do you want to propose?
Well, it takes less work to like the energy level that is required, like the activation energy.
Okay, stop right there. So it's going to take less activation energy. So what that might mean here is that if I was to draw this diagram, that means that the activation energy to form the secondary might be higher than to form the tertiary. But that's what has to be the case, right? Activation energy gives you the rate. The rate equals A times minus E to the minus EA over RT. That's the Arrhenius equation. The Arrhenius equation is the mathematical relationship between rate, activation energy, and temperature. It's a logarithmic function, but this is where we get our trends. Lower activation energy, faster reaction. Higher temperature, faster reaction. But that's the mathematics of it. So this kind of diagram is actually what happens. But it's not a trivial thing. For instance, in general chemistry, you were probably cautioned that energy and kinetics are two different areas. And they may or may not be linked. I'll give you an example. If you calculate the delta G, which tells you whether a reaction is spontaneous or not, of a diamond going to graphite. Graphite's going to be your pencil lead, right? That reaction is spontaneous. It is predicted to occur, okay? Now, if you have a diamond, you don't need to get all freaked out that your diamond just one day is just going to go poof into graphite dust. The kinetics for that process are slow. But thermodynamically, it's predicted that that would happen. That's spontaneous. So we have to exercise caution in taking thermodynamics and relating them to kinetics. So the person that came up with this relationship that we're going to use is Hammond. And then it's the Hammond, in your book, I think it's the Hammond-Leffler postulate. I know where Leffler came from. I think he might have modified this for like organic chemistry. And what Hammond's postulate truly says is that the more stable the products, and in this case going from reactant to intermediate, is the intermediate's the product. Going from that, the more stable you make the product, the more the reactants look like, or the more the transition state looks like the products. Okay. Reaction coordinate diagram. Reactants, products, they have equal energy. We know that the more stable, sorry, I completely messed that up. I'm going to say it again. When you move the reactants products, when you move the products to be more stable, look at how the transition state's moving. Where's the transition state moving towards? This side. It's moving towards the reactant. So I said that completely wrong a minute ago, but forget it. When you have a more stable intermediate, that means that the transition state looks more like the reactants than the products. So when you have a more stable product, the transition state looks more like the reactants. And conversely, if you make the product less stable, what happens? The transition state begins to move towards the products. Now, what does that mean? In Hammond's world, what it meant was that the more you can make the transition state look like the reactants, the less energy you have to spend to rearrange the atoms to get to the transition state. And the less energy you have to spend, the quicker that can occur. But what it really means is, it really means that the activation energy is going to be lower. And if you make the intermediates less stable, it's going to take more time and energy to get to the transition state. And that's going to increase the activation energy. So what we do is we take Hammond's postulate and we basically say that the more stable the intermediate, the lower the activation energy. We then say lower activation energy. The Arrhenius equation then predicts that the reaction will occur faster. And so the entire reasoning, and I used to ask this as sort of an essay question on exams when I had less than 70 people to grade. It's not out of the question, but it's probabilities decreasing every day of asking this. But here's the reasoning. Okay. Why does a tertiary halide react faster in an SN2 reaction? Number one, tertiary halide's more stable. Why is it more stable? Because it has more alkyl groups pushing electron density into it. Okay. So what? The more stable the carbocation, since the carbocation is in the rate determining step, the lower the energy of the intermediate in the rate determining step. So what about that? The lower the energy of the intermediate, by Hammond's postulate, the lower the activation energy. The lower the activation energy, Arrhenius equation says that reaction will occur faster. If the carbocation wasn't in the rate determining step, I wouldn't be able to make all that relationship. So that's the true reason why the tertiary carbocation is going to react faster than secondary, because it's more stable. It's in the rate determining, carbocation is in the rate determining step. The more stable that intermediate is, the lower the activation energy, the faster the reaction. So that might be a little bit of layer of unnecessary detail, but you're going to get it anyway. Okay, because that's what we have to understand about this reaction. When I did an SN2 reaction, you might have said, well, why didn't you talk about any of this? Well, because there were no intermediates, right? There was just a transition state going to the final products. What was the important part of the transition state there? The steric hindrance of that nucleophile coming in and attacking the carbon. That raises and lowers the activation energy because it raises and lowers the stability of the transition state. So actually in an SN2 reaction, I could make the product more or less stable, but that's not the reaction. The reaction is that initial steric hindrance, and that's what causes the activation energy to go up and down, not the stability of the products. In SN1, it's the stability of the carbocation intermediate that drives whether the reaction goes faster or slower. Okay. So that's the complete picture of SN1. Now, I'll give you your graded assignments that I have. There is a next graded assignment is going to be to write the mechanism of an SN1 and an SN2 mechanism. This will be due next Monday. The SN1 mechanism in here is with a neutral nucleophile. I decided to finish up with the Hammond's postulate, then write the mechanism out completely. I did do the entire mechanism in the morning class. So in the morning class, they're getting Hammond's postulate, and on Friday, we'll talk about what you do when you react something with water or alcohol, the solvolysis reaction. I will talk about that, and then we will continue our discussion, solvent effects, all of that on Friday. If you're overly ambitious go-getter student who wants to work on that problem right away, you could go to YouTube and find the morning class and watch that, which is actually the same as some of the other videos I've done. So you can try it, and then I'll go over, not this one, but I'll go over another one on Friday, okay? So pick one of those up, and I've got these in alphabetical order, so